Good afternoon, everyone. My name is Haseeb. As you can see on my screen, I am a Group Cloud Custom Engineer. Uh, so a bit about myself and why I got engaged in this activity. So I did my PhD in machine learning in 2009. So I have been working in machine learning for the past 9, 10 years, even though this is not my focus area anymore, but still this is a topic which is very close to my heart. I wanted to make this session as interactive as possible. And again, not knowing what the skill set of different people is, I wanted to touch upon or give a very light into the machine learning as well. So again, if you feel that's not necessary, just drop me a ping and I will hop along. I will jump to the next section. So I will be able to check my chat messages off and on. I'm using a single screen over here. And if you don't hear me well, just give me a shout out. Right. So the purpose for today's workshop or the talk is that I wanted to share some learnings. And again, I have been on both sides. I have been working in companies where I had to work on designing machine learning algorithms, and I have been on companies where I was doing my own startups and I had to deal with all those complications myself. There were lots of mistakes that I did in my own journey, and there are lots of mistakes that we see customers doing as well. So my idea was to sum up or distill all that knowledge into a process for machine learning, which can not only help you, for instance, frame a problem, qualify a problem, but also think more around how you can make your machine learning solutions production grade and so on. And again, it doesn't need to be a very extensive work in terms of machine learning. You can, of course, take some small steps. You can create some very viable, minimum viable projects. But I think going through some key concepts, some key elements would be helpful. So I'm just going to check my message again. Let's go here. So I wanted to cover today a very light intro to machine learning. And of course, we cannot cover all the concepts, but just to give you guys enough idea as to how you can get started on machine learning. We will talk about feature engineering and model selection. Both in my experience and the mistakes I see customers doing, this is one element and one area which everyone, I think, lacks a lot. So they jump on designing a machine learning solution without understanding their data, without understanding the intricacies of feature engineering, and so on. Then I will talk about Cloud Machine Learning API, pre-trained selection of machine learning models from Google. I will talk about Cloud AutoML, the way you can easily develop custom machine learning models. Then I'll talk about Cloud AI Platform, a fully extensive data scientist-centric platform for data scientists, to develop applications. I will talk about Cloud AI Hub for the sake of collaboration of ML assets. I'll also talk about Kubeflow and MLOps. So starting with a very light introduction to machine learning. And as I said, that this is a mistake that I did myself, and this is a mistake I see lots of people doing. And the mistake is that we never try to qualify and we never try to frame a problem into a machine learning problem. So for example, this is a very simple example. We have a machine and it has a simple rule. When the power is turned on, start sweeping. And my question always is this a problem that we can frame into a machine learning problem? And the answer is no. This is not the sort of problem which machine learning is designed for. And the reason is that from our traditional programming, which we all do, we are used to creating rules. We create heuristics. We create recipes. We ourselves know what those rules are. And then based on those rules, we design our applications. That's not the intent of machine learning. The intent of machine learning is that it has to find patterns in your data. And again, most often, those patterns are not visible to us using our naked eye. So for example, we might be dealing with massive amounts of data. What's the relationship between different data points? How feature or a variable A can affect variable B? How variable B can affect the outcome, and so on. So those patterns is what machine learning is all about. So we have to help machine learning because machine learning only learns by example, not through rules, right? Of course, I mean we will apply a certain level of rules, and this is why I wanted to focus a lot on feature engineering and data extraction. But still, we let the pattern finding to machine learning. A very simple and overused example that you have thousands of examples of cats images, thousands of examples of dogs. Now, it is extremely difficult for us to create or infer rules that given an arbitrary image, we can apply those rules and figure out whether that image is a cat or a dog. This is where machine learning has to come into play. So compared to the first example where we had a bunch of rules, in this case, we cannot create rules and we allow machine learning to find patterns by itself, and we allow machine learning to find those rules for us. So this is a simple classification problem. Given any unseen image, cat or dog, a machine learning model should be able to predict whether this image is a cat or a dog, right? So I generally use a very simple checklist. So when anyone comes and talks to me about machine learning, I ask them these 5 questions. So first of all, can we use any heuristics in your problem? If we can, I would say let's start from there. Do not start from machine learning, start from heuristics first, right? Anyways, we would like to know heuristics if you want to understand our data a bit more. And then my second question is, or my remark is that machine learning is about automation. If you're thinking about a task that can be handled manually, I would again advocate against using machine learning. And then, of course, there are some reasons, and I will cover those reasons in a bit as well. And third, I think which is also extremely important, a mistake that we see customers doing. I did the same mistakes as well. That machine learning will never be precise. It will never give you 100% accurate results. So if your application is not prone to errors, if your application cannot handle errors, then machine learning is not a good backend candidate solution. And then it's a matter of transparency. Even though, I mean, now there are tools using which we can understand how a machine learning model has evolved, what it has learned. We can even reverse engineer a prediction back to underlying machine learning model, but still it's not transparent enough. I mean, of course, rules are way more transparent. We can see, okay, why an application recommended to do things in a certain way. Machine learning model, on the other hand, hides lots of the complexities in itself. And lastly, do we even have data? Because everything is driven by data. However, this point can be debated because now we have lots of pre-trained models already. But if you want to build a custom model with your custom data, then we need to have data. So given these 5 questions or 5 checklists, I always try to frame a problem into a machine learning problem. So let's take an example. So I think most of you guys have used Gmail. So Gmail gives you a notification. So for example, if you forget to attach a file, it gives you a recommendation. And I mean, I also used to think that it's driven by some sort of a machine learning model, but the truth is that it's based on heuristics. It was a very crude, rough recipe. Of course, it has refined over the period of time, but that recipe was simply looking for keywords like attachment or attached and so on. Now, the key takeaway is that, I mean, experience can still feel smart or personalized without ML. So in this case, there's no ML involved. Of course, an ML system probably would catch, I don't know, more potential mistakes, etc. But it's way more costlier to build and to maintain as well. So again, from an experience standpoint, machine learning is not always the only solution. Now, we talk about those 5 questions or that checklist before we frame any problem. But there are some additional questions that we should know. And again, I mean, this is a very light intro to machine learning. So bear with me if you think it's too basic. First of all, what do you want to solve? Do you want to solve a classification? I mean, cat or dog, class A or class B, positive result or a negative result? Or do you want to regress on a specific value? It means that we want to predict I know the forecasted selling price of a house. If we have 1,000 example data sets of historical sale prices of houses in the same area, then what type of data do we have? Are we dealing with images, audio, video, meaning the completely unstructured data from which it's very difficult for us to infer a structure or pattern of our own? Or are we dealing with tabular, structured, labeled data? Whatever the data is, before starting, I always ask everyone to look into what features are important to you. What shall be the input to your machine learning model? And we will talk about training servants queue in a bit. So I think this point will be much more clear. But point being that unless we know what data we have and how we can use that data to predict something, I think we are probably going in the wrong circle. Lastly, what algorithm shall we use? Now, this is a very extensive topic. We can't cover that in this session, but I will just give three examples over here. So for example, we are dealing with regression. We want to regress a numerical value. We have structured tabular data. So we're dealing with a linear regression. To understand machine learning in a very basic, crude way is that we have a feature represented by X, and we have a value Y that we want to predict. And machine learning model will try to figure out weight and bias to satisfy uh, or figure out a curve or a line which can pass through my example data set. Right. So in this case, I have lines of code as my feature, and I have a number of bugs which I want to predict, and the machine learning model has to figure out what shall be an ideal weight or an ideal bias so that it can mimic or it can represent the structure of my data points. Right. Again, this is a very simplistic example. These are referred to as learnable parameters. And the way it happens is that machine learning model will iterate. And then again, I'll talk a bit about hyperparameters, how this learning process can be governed, etc. today. But essentially, it will try to figure out what is the ideal weight and what's the ideal bias or intercept in this case. In this case, it says 0.82 should be the weight for my feature lines of code, and 5.8 is my y-intercept or bias in this case. Again, maybe it's good, maybe it's bad. There are some metrics that we have to look into whether this model is good enough. Moving on, if we're dealing with a classification problem, classifying an output as a class A or class B, and we're dealing with a structured tabular data, then we are dealing with logistical regression. It's very similar to linear regression. The only difference is that we have to pass the linear regression through a sigmoid function. I think this is something that you can look up yourself. Essentially, we are creating a thresholds over probability. And if the value is above a certain threshold, we classify output as class A, for example. Otherwise, we classify it as class B. And this is not the only function. There are a number of functions that we can employ for logistical regression. Very quickly, and this is something, the reason for mentioning this is that this is one area where I learned the hard way that we were always taught that if you have a categorical data, since machine learning model will try to find out weight, it means that that feature should be multipliable. So you have to convert that into a numerical data, for which we use one hot encoding, we create feature vectors, etc. There's also a reverse process as well. And this is the reason why I'm mentioning this over here. So I will cover that aspect. So keep this in mind. I will cover that in more detail when we talk about feature engineering. Similarly, if we're dealing with classification, but we have categorical data, then we're dealing with decision trees. Again, a very simplistic example of a decision tree. So bear in mind, I mean, this is probably like last couple of slides where we're talking about these basics, and then we'll move on to something more fun. And lastly, neural networks. Neural networks or deep neural networks, when we're dealing with rich, unstructured data, photos, audio, video. And I mean, one fun way of describing neural networks is that when you don't know what to do, you probably will be working with neural networks. And this is where you are hopefully expecting magic to happen without knowing what's happening. But in essence, one way of visualizing or thinking about neural networks is that think about a problem space which you cannot represent through a single line, single curved line or single straight line. Maybe you need multiple lines. And how do you do that? You need to have multiple learners for those purposes, right? And this is essentially what, in essence, neural networks does. So in case of, for example, these images, it might create multiple layers, each layer working on probably a certain feature. So for example, if you're creating a convolution neural network, maybe the first layer would be converting the images from RGB into grayscale, maybe. Maybe the second image is taking care of a shape of eyes. The third layer might be working on the shape of ears. The fourth layer might be working on the dominant color on the base input data. We have to activate all those different layers and so on. So essentially, it's a combination of a bunch of weak learners. And this is where a bit of confusion comes into play as well, because we also have ensemble methods, which is also by definition a combination of different weak learners. But there is a very clear distinction between those two methods. One good learning area would be to look into TensorFlow Playground. There you can see a bunch of different examples of essentially around classification, and you can play around with tweaking number of layers, number of neurons, trying different activation functions, and so on to see how neural networks work. Right. So now I think let's move on to a slightly different speed. So um, whenever you are dealing with a machine learning problem, so always remember that machine learning is not just a glorified curve fitting algorithm. It has to provide an acceptable level of generalization. Now, think about it like this. For example, you have 100 examples, right? And you pick up arbitrarily, randomly 80 of those examples. Now you train the machine learning model in case of, for example, a linear regression to try to find out that line or curve, which will try to go through those different 80 different data points. Now, the generalization means that that model should work against my test data. So we have 20 examples which we never used for training purposes. And then it should also work for unseen data. Now, unseen data is one aspect which let's park till end of this talk, because this hasn't been formally or properly optimized till today. Now we have more like a DevOps-like approach where we can create a feedback loop in which it's possible to handle the performance metrics, for example, data drifts, any training serving skew errors, and so on. But prior to that, it was a lot about hit and trial. So looking at these examples, so we have two examples over here. We have X as a feature, Y is the output that we want to figure out. In this case, we have yellow circles representing my example data points, and machine learning figured out two different lines. One is a horizontal line on the left-hand side, and one is a line with an angle on the right-hand side. So how does machine learning know which of those lines is better? This is where we have to bring in the notion of cost function or loss function. Now, in this case of linear regression, things are rather simple, because we can figure out the Euclidean distance between the predicted line or the line which machine learning proposed, that blue line, the actual data points, and then just simply square them and just create a mean of those. And given those, I mean, the line on the right-hand side gives less error, so we deem that more appropriate or a much better model. So another way we can think about machine learning as an optimization of weight, W in this case. So it would try to find a local minimum by iterating over different values of weight, by essentially reducing the cost or loss function, right? Again, so I gave just one example, but how about, for example, classification problems? Because in case of classification, we cannot find that Euclidean distance. So for that, we have to deal with probabilities, and for that, we use cost entropy. So I will just again leave this as a self-study to figure out how you can design or which cost functions are available when you're dealing with classification problems. Now, rather quickly, we talked about machine learning as a way to figure out those weights and biases, intercepts, etc. for different features to minimize the cost function. And the way it does is through a very simple, rather simple function called gradient descent. So it just tries to minimize along the negative slope, tries different values of weights. And the reason for, in fact, mentioning this is that this learning is governed by a parameter called learning rate, right? So if we give a large learning rate, so as you can see on the figure on the left-hand side, so machine learning model will very aggressively change the value of weight. And that can result in a situation where instead of going towards the local minimum, we are increasing our error rate. On the other hand, if you give a very small learning rate, it will converge, but it will converge with lots of iterations. And reason for mentioning this was that these learning rates, and again, there are lots of those external configurations. So this learning rate is outside the actual mechanics of our machine learning model. This learning rate is referred to as a hyperparameter. Let's say we are dealing with decision trees. How many levels shall we have? If we're dealing with random forest, how many trees shall we have in the random forest? All these are hyperparameters. If we're dealing with neural networks, how many layers of neurons shall we have? How many neurons shall we do? And so on. So I mean, there are lots of hyperparameters. So as when you are solving a machine learning problem, I mean, aside from figuring out a good machine learning algorithm, you also have to think about these hyperparameters. And again, I just gave an example of gradient descent. There are many more learning methods as well, which probably you won't be using. But let's say if you are dealing with a situation where you want to have more mathematically proof way of learning, you can go with a method referred to as Newton, which is a second order derivative. It's more mathematically sound, but it can create those saddle points, essentially meaning that you will never converge. So it's possible that you will never converge. And as also it's computationally quite intensive. So again, point here was that there are some parameters outside machine learning you also have to consider. Now, we talked about generalization. We talked about splitting our data into training data, into our test data, and then we also have an unseen data, etc. So formally, we can say that machine learning is an optimization problem. We want to minimize our learning error. So essentially, I mean, the example I gave around mean squared error, where we want to minimize the mean squared error of that line against the example data set. And then we have a generalization error, because when we train that line, when we train that model, we will subject it to our known examples. Remember, we talked about 20 examples that we picked aside. We never use them for training purposes. We will use those examples now to see what's the generalization error. Now, if we keep iterating long enough, what will happen is that we will go most likely to an overfitting scenario where we end up creating a very complex line, which will try to cover all those data points very crisply. That means our mean squared error would be close to zero. It means that we don't have any bias in our data. It means that our data fits or represents, our model represents our data point very crisply. However, what will happen when we will subject it to examples that we know it hasn't seen before? What about the generalization error? What about the error rate when it's subjected to completely unseen data? So that's not a very good way of training a machine learning model. Similarly, on the other extreme, you have underfitting. Your model is so simple that it has a very high learning rate, right? So essentially, I mean, this optimization problem will try to figure out a balance of learning rate and a generalization rate. And so when you start working on machine learning problem, you need to understand, I mean, at least these concepts of cost functions very clearly. You need to understand the concepts of variance, bias, underfitting, overfitting, area under the curve. I'm just throwing out lots of words over here. Precision, recall, what are true positive, what are true negatives. And again, I mean, my idea here was to just give some basic foundation, and you can just then start exploring on your own. Another way of looking into this problem is that if you look into the overfitting example, it's a highly complex line. I mean, a very oscillating sort of a line. It has a low bias because it's not biased towards any data. It has a high variance, of course, because it's changing as my data is changing. but it will most likely capture a lots of outliers as well, because outliers are the cases in which we know that data should not be included. And this is why, I mean, feature engineering becomes important, because uh, in order to satisfy outliers, we might end up in an overfitted scenario. However, if we do an underfit scenario, we will have a model which will which will have a very high bias, which will have a bias toward, for example, cluster of data. So it's a fine balance that we have to figure out. And again, there are some bunch of approaches. When you, let us say, look into TensorFlow Playground, we also find the concepts of regularization, which essentially introduces biasness in your model, which is counterintuitive, but in some cases, it's extremely relevant. So, I mean, okay, so let's just think about one simple example. So let's say we're training a machine learning model, which will try to predict conversions from leads. And now assume that our training data set had all the leads converted when they came from California, for example. Now, machine learning model will learn, and it will give an extremely high weight to location, because it knows that if the location is California, then I know that the leads will get converted, right? So in those sorts of cases, we would like to penalize machine learning model, and we need to avoid giving some specific feature too high of a weight. So again, that's where, I mean, we self-induce the biasness in our data. But I mean, those things can be covered in a much better way if we are extremely careful with data preparation and feature engineering. So I think, I mean, I would probably take this, let's say, a segment, and this is I mean, what I have learned through hard way. This is where I see, as I said in the beginning, lots of customers and practitioners making mistake, because the biggest impact to machine learning project is not using the best optimization algorithm, or making a very deep neural network, or creating a very smart loss function. It's all about the quality of your data. I mean, so think about it this way. Machine learning is already not very transparent. So imagine that you have given machine learning 10 example images of cats, but they were labeled as dogs. Now you will spend numerous hours fine-tuning your machine learning model. You will start playing with different layers of neurons. You will start playing with hyperparameters, but your input data was not really correct. So if your data is not reliable enough, all your effort would not be very useful. So that's why, I mean, feature engineering and data engineering, they are one of the most important topics. So I mean, we used to say within Google that 80% of basically 80% of the time will be or shall be spent on data engineering, and the remaining 20% should be spent on developing a machine learning model and making it scalable, etc. So what do we mean by that? So we mean, first of all, that we need to create a quality metrics for our data. I mean, that includes, I mean, some very, very basic things. I mean, whether our data is reliable or not, how do we represent our features, and how do we minimize skew? So for example, making sure that there are no labeling errors. If there is noise, we should not introduce noise to machine learning model. If there are outliers, can we detect outliers and can we take them out? Maybe we have done wrong sampling of data, and we are expecting a model to do something which our data doesn't even support. So reliability of data is extremely important. Then most often or not, you will be working in situations where you have data, but that data needs to be mapped into features. Right. So for example, I mean, just let's just take a very simple example, right? I mean, I have been to a certain location. I have been to a certain cafe 5 times, um, and you want to maybe create a feature that this person likes coffee, for example. Right now, this feature is not available readily in my data, so I have to map data into features. So I have to be a bit smart, a bit creative when I map data into features. And again, good feature representation will be the key for a good model. And then lastly, minimizing the skew. I mean, it's a very overused example, but think about it this way, that you are working on a classification problem and you give it 1,000 images of dogs and you only give one image of a cat. Your data is extremely biased. You have to minimize that skew as much as possible. Now, it does not mean that we synthetically take out 999 images of dogs, because yeah, because that's the reality. For example, I mean, this is the reality of my system, where I get data for a certain class way more than the data for some other class. But there are ways where we can minimize that skew. The important point being that we need to be extremely careful about the quality of my data by creating a quality matrix around reliability, feature representation, and the skews. Second mistake, which we see happening very, very often, is not clarifying the assumptions. So, okay, so think about a very simple problem that we want to train a machine learning model, which, given the number of customers, predicts the possible revenue. I mean, this looks simple enough, but the problem is that the feature number of customers is not available when we want to do prediction. So let's say we want to get a prediction Thursday morning. We don't know how many customers will there be on Thursday. We will know that number at the end of Thursday or Friday. But at that point, prediction is useless because we have the actual revenue already. And the problem is that we made an assumption while training a machine learning model that we will have this feature available when we are doing predictions. So this is referred to as training serving skew. And this is where, I mean, I see lots of mistakes being done. So quality, quality metrics for your data, and making sure that whenever you are training a machine learning model, clarifying the assumptions as to what features are available at the time of training should be the same as the features which are available at the time of prediction. Right. Once that part is done, then we have to carefully label our data. So for example, I mean, as I mentioned that in some cases we'll have direct labels. In some cases we would have to derive labels. So user watched a video from Taylor Swift. He's a fan. This is a derived label. Same applies for events and attributes as well. So think about events, start labeling those events. If you think about attributes, start labeling those attributes. So far, so good. Now things get slightly more interesting. Now we have a quality metrics, right? We have labeled our data. We have clarified the assumption, and we are sure that we will not end up in a situation where our prediction expects something which is not available at the time of prediction. Now, how do I train my model, or how do I sample my data? Let's think about a search example. So we can do a bunch of different ways. So shall we pick random queries? Shall we pick random sessions? Shall we pick random users? And the answer is it depends. We need to understand what we want to do with that data. So let's say if you want to use a feature previous query, we need to sample the data at a session level. If you want to, I don't know, understand user behavior, then we have to sample at the user level. Again, the point being that unless we know what we want to do, we can end up creating or getting data in a very wrong granularity. And once we have established the granularity of our data, and I talked about the data skew or imbalanced data. So again, think about it like this, that you have, I don't know, 100 negative samples and you only have one positive sample. So your minority class is a very small proportion of your entire distribution, right? And I mean, practically speaking, you will never have a perfect distribution, right? You will never have a system which generates data which will have equal 50% each for two classes. You will always have some degree of imbalance. But I mean, if you're dealing with an extreme imbalance where less than 1% of your data set is minority class, then your data is extremely skewed, extremely biased towards your majority class. And this is what we have to avoid. So a very simple strategy, and this is not the only strategy that you can use, is that you can downsample the majority class. So for example, in this case, we have 200 negative samples and we only have a single positive sample. So we are dealing with an extreme degree of imbalance. So what we can do is that we can do a downsampling factor of 20. We pick 20 negative samples and we do not change positive samples at all, right? Looks good, but now we have introduced biasness in our data. This doesn't represent my reality. My reality is that I only get one positive sample out of 200 negative samples. And how do I do that? Now my distribution looks slightly better. So my machine learning model will not be biased. I mean, it will still be biased, but not be as biased compared to the first example. But how do we deal with the bias I have introduced by cherry picking a sample of my data? Is that I upweight the majority class with the same downsampling factor. So again, I mean, this is not the only approach. There are other approaches as well. The point here was that we understand what we have to sample. And when we sample our data, we need to be careful around data skews. If we have data skews, our model will become biased. We have to take out that biasness by maybe introducing biasness of our own, but there are ways in which we can control that. Now, we have quality metrics in place. We have identified features. We have the right sampling strategy. We have make sure that our biasness is in control. We don't have much of a data skew. Now we talk about splitting that data. So practically speaking, make your data generation pipeline reproducible, because you would be working on multiple machine learning models. You'll be trying out different types of machine learning models. So making your data generation pipeline reproducible will be helpful. I mean, you can just seed your random number generators, or you can use hash keys, for example, etc. So I mean, hashing is in fact like one good way that you can use. It's not very complex. The only thing I would say about hashing is that make sure that when you're hashing, use some additional attributes. Otherwise, I mean, you can be in a situation where you are hashing, splitting your data, everything looks good, but all your data for the same class is going to the same bucket, same split, which is not ideal. So assume that you are training your machine learning model. Your training data set contains all the data from class A, and then your validation data set contains all the data from class B. So hashing is good. Hashing takes the randomization or reproducibility aspect out of equation. However, make hashing a bit more unpredictable by introducing something like query time or some other additional attributes. Right. Okay. Now, this is probably one of the most important things which you would like to do when you are, I mean, before training a machine learning model. And there are different types of transformations. So you can either, for example, I mean, you either have to do some mandatory transformations. So for example, like categorical data to numerical values, because they have to be multiplied by the machine learning model. If let's say you are working on a convolution neural network, all the images should be in the same resolution, right? Same goes for normalization of data as well. And then there are some optional transformations, meaning that, I mean, making all your text in a lowercase, introducing some sort of a non-linearity in your feature space, and so on. So let's talk about the mandatory ones. And again, I mean, this is I wouldn't say that it's completely mandatory, but they are very helpful. So let's talk about transformation of numerical features. So there are essentially two different ways you can do that. You can either do a normalization, so bringing the numerical value to the same scale, or you can do a bucketing. Now, bucketing is in fact counterintuitive, because we talked about transforming categorical features into numerical values. But now bucketing is all about transforming numerical values into a categorical data. So I will explain that in a moment, because it's counterintuitive in the beginning. But first of all, normalization. So think about it like this, that you have raw data of this sort. I mean, again, this is not obvious from the last four images, but let's take it like this. We have raw features. It doesn't look very uniform. I mean, there might be skewness and biasness in this data. That can be problem number one. Problem number two can be you might be dealing with lots of outliers. Problem number three, your data might be subject to a power law distribution. It means that it's very biased towards very select number of cases, and so we have to figure that out. So you have a bunch of different ways. So let's say the first approach is that you scale your data to a range. So let's say, I mean, in this example, what we're doing is that We have 5,000 to 1 million. We know the lower bounds and upper bounds already. We know everything is within bounds. So we shrink or we stretch that feature value to fall between value 0 and 1. This is like one approach that we can take, in which we scale our data to a specific range. Now, even more interesting is the feature clipping. So let's take a good example. So in this example, as you can see, that we have rooms per person, right? And we see a long tail in which there are more than 10 going up to 60 rooms per person. They are definitely outliers, right? And due to these outliers, our distribution looks very strange. Now we know the upper bounds. We say, okay, a number of rooms per person cannot be less than 0, and it cannot be more than 4, for example. So we collate or we aggregate all the data beyond 4 into a single point. So now our distribution looks much better. So what we have essentially done is that by introducing the upper and lower bounds, we have taken out outliers from our data. Now our data looks way better. Second, so again, I mean, you will probably be using a bunch of those approaches, not a single approach. So let's look into log scaling. So in terms of log scaling, we want to compress that data to a specific range. So for example, let's look at an example of ratings per movie. In this case, I mean, we have a very small number of movies with a very high ratings, but the long tail contains a very small number of ratings. So in this case, we use log scaling. Because I mean, this is a typical case of power law distribution where log scaling can be used, and now our distribution looks way better. There are also some approaches in which you can use z-score. The idea here is that we don't have extreme outliers, but we do have outliers. And what we do is that we create the mean, and we define a threshold that we will only take data which is plus minus my threshold. So I will ignore all the data which is outside my threshold. So that's why, I mean, I'm essentially pivoting my data around my mean. So that way, I mean, I can be sure that I will not be taking any outliers. So idea being is that you can improve your distribution to a great deal if you follow these normalization techniques. Now, then we talked about transforming the numerical data into categorical data. This is where the bucketing comes into play. So for example, think about latitude, longitude. It intuitively looks okay, but think about it, latitude 37, latitude 38, what does it really mean? When we apply a weight to that latitude number, what does it really mean? And maybe when we're talking about latitude, longitude, we're talking about locations. And maybe, I mean, having such a fine granularity is not really relevant for us. So we just bucket them together. When we bucket them, we index them. This is what we refer to as taking this numerical data, transforming it into a categorical buckets. Of course, they're indexed so that they can multiply, but now they make much more sense. You can even optimize that by creating buckets based on quantiles. It means that all your buckets have the same number of data points. Similarly, you can transform your categorical data. So for example, I mean, you have categorical data, you can create a vocabulary. You can create auto vocabulary, sort of a catch-all sort of a clause. The problem with this approach is that you have to build the vocabulary up front. You have to build the index for your vocabulary elements up front. For that, you can use, of course, hashing. Hashing is not is not collision proof. So you can have, let's say, at index 4, frequent and woman, at index 7, these and terms. So it's not a good solution when your terms are extremely important and you want to take those terms separately for the sake of feature multiplication. You can use, I mean, a hybrid of hashing and vocabulary. So for the critical items, you can use vocabulary. For the less critical items, you can use hashing. To quickly sum up, feature engineering is extremely important. So we talked about the quality metrics. This is extremely important. You need to have a good data. You need to understand what exactly is your sampling strategy that depends on what you want to do with your data. You should clarify your assumption. Try to not have any training serving skew. Split your data with some sort of a random sampling which is reproducible, and then do transformations of your data, meaning that you can work on improving your data distribution a great deal if you look into different normalization strategies. And in terms of types of machine learning models, again, this is a very, very simplistic view. You will find many verbose views on the internet already. If you're dealing with a simple data, than we are in classical machine learning. If we're dealing with complicated data, unclear features, we believe in miracles, etc., then it's neural networks. If we're dealing with the low quality data, where we know that our data has a lots of bias and our resulting model can have lots of bias, one approach is that we do not ask machine learning model all the questions, meaning that we limit the exposure to data, we limit the exposure to features. We create very weak learners, and then we combine those weak learners, which have the capability to have low variance and low bias, into an ensemble method, like let's say, a random forest. And in cases in which you don't have data, but you have an environment, you have an agent which can interact on your behalf and provide feedback, positive and negative feedback, reward-based system. In that case, you can have a reinforcement learning. So that was, yeah, I think that took longer than I expected. So moving on to how we approach machine learning. So machine learning is in the DNA of Google. So all of our services have machine learning in one way or another. So you can expect machine learning everywhere. And what we're trying to do is that we are trying to make sure that all these learning services, algorithms, they are available for everyone as well. So first and foremost, we have Cloud Machine Learning API. So I'm going to skip this one for now. So Cloud Machine Learning API, these are pre-trained machine learning models. So you don't have to bring any data, work on distribution, etc. Those models are trained already. So you have models for speech, models for video intelligence, models for cloud vision, etc. So I'll just give an example. Very recently, I was given a problem that we have images of a construction site, and we want to figure out through machine learning if the construction site, if the walls in construction site are finished or not, or if they're not finished, which stage they are in. So it means that we have to figure out how many, for example, what's the material available in those images. Uh, Whether we have a metallic scaffolding, whether we have a wooden scaffolding, whether we have plaster on the walls, and so on. And our first idea was, okay, we have to create a very complex machine learning model. But we said, okay, we don't know what that data really means. We don't know what features we can extract. So we went to Vision API. Vision API, out of the box, without us training or writing even a single line of machine learning code, gave us lots of things. For example, which material is part of those images. So it told us that there is metal over there. It told us there's fire. It told us that there are humans over there. There's a helmet over there. There is a welding machine over there, and so on. So it gave us lots of those features out of the box. So, and that became essentially our input. So when we ended up creating a machine learning model, we took the input from Vision API, which did lots of things on its own. We didn't have to do all those things ourselves, and we created this hybrid sort of a model. So point being that without doing anything of our own, Vision API gave us lots of things. Of course, it was not a custom model. Our requirement was a custom model to detect the life of a wall and how close it is to completion. So for that, we had to do something anyways. But Vision API gave us facial recognition, material recognition, dominant color, OCR, etc., out of the box. So it was a very good starting point. Cloud Speech API, similarly, you have 120 different languages. You just build up an application to do a real-time translation of audio. Cloud Speech API will work perfectly fine. Unless you want to work on some very, very specific accent or a language which we don't support, Cloud Speech API would work perfectly fine. It will detect inappropriate content. It has a good level of vocabulary. It will handle noises, etc. So again, all the hard work has been done. These models are trained with enormous amounts of data, and we in fact use these models ourselves in our services too. Similarly, Natural Language API, so you can get semantic structure, entity recognition from your text, and so on. You don't have to do much over there. Video Intelligence API is something extremely interesting. So I worked with a customer that they were trying to develop a sensor-based solution for self-driving cars, right? So, this is like our first point of experimentation. We said that, okay, we want to figure out how many frames there are. We need to figure out when those scenes change, what happens in a frame. Do we see a traffic light within a frame? Do we see a moving object, and so on and so forth? And all those things can be extracted through Cloud Video Intelligence API. So it will tell you when your shots change, objects within those frames. It works on a 1 frame per second model, different segments of your videos, and so on. So again, without doing anything, pre-trained models work best. Translation API, I think you all have used Google Translate. It's the exact same service available as a machine learning pre-trained model as well. So the point being that these machine learning APIs are excellent for cases where you don't want to do machine learning. I mean, of course, you want to do machine learning, but you don't want to do machine learning from the beginning. You just want to understand the structure of your data. I mean, let's say you have images, let's say you have a video, and maybe you don't even know the possibilities of what's possible. So that's a good starting point. I mean, we see lots of applications being developed through APIs alone. They don't need any custom model. I mean, if that's the case, that's perfect, because you're not concerned with training those models. You're not concerned with deploying those models. You're not concerned with serving those models. You simply have to provide your data. Moving on, moving slightly up in stack, we have Cloud AutoML. Now, the idea of Cloud AutoML is that it's an algorithm which will generate the machine learning model for you, right? So, I mean, typically, whenever, let's say you want to, I mean, again, the reason I mean why I was talking about training service queue, I was talking about hyperparameter tuning, selection of a machine learning model, etc. You're not concerned with any of those things in Cloud AutoML. Compared to machine learning APIs, you want the model to be custom based on your data. However, you're not concerned, or you let the service decide. So the service will essentially do an exhaustive search. It will try maybe 5 different types of machine learning models. It will try to figure out which model works best. It will try to compare metrics, and it will just give you a trained machine learning model. So you have not done any pre-processing. You have not done any model tweaking, hyperparameter tweaking. You have not done any infrastructure management around deploying and so on. You have simply provided your data to Cloud AutoML, and it has taken care of all those aspects of your own. So simply put, you give your data set. It can be tabular data, it can be image level data, or whatever it is. AutoML will try to figure out the best model. It will train that model. It will deploy. It will serve that model, and you will simply be consuming that using REST API. So, in case of machine learning API, you are only consuming it with REST API. In case of AutoML, you bring your data. You create a custom model. Of course, I mean you can see what the model looks like, all the metrics. You can iterate over different elements of that trained machine learning model, but AutoML will hide all the complexities of that specific machine learning model. And this is exactly what we did, the example I was giving earlier. So we created a multi-class classification for walls. We took the input data from Vision API. We created this AutoML machine learning model, and I think in 2 days, we ended up building up a solution which could detect the life of the walls. Otherwise, we would have spent months figuring out data, machine learning model, tweaking it, and so on and so forth. So again, I mean, things can be done in a rather simple way. So it's good if you have limited ML expertise, but you want to have your own custom models, and you don't want to deal with all the complexities of training machine learning model yourself. So that's a good solution from those perspectives. And then Google Cloud AI Platform. This is where you have the full flexibility. This is where you have you are served as a data scientist. So if you're a data scientist, you want to do pre-processing of your data, sampling of your data, you want to create your own notebooks, you want to work on your own custom images for deep learning, you want to decide whether you want to use TPUs, GPUs, CPUs, you want to do the labeling yourself, you want to manage the infrastructure yourself, and so on and so forth. This is where Cloud AI Platform kicks in. So this gives you that full freedom of designing your own algorithms and so on. So what essentially is Cloud AI Platform? It's essentially 6 different services. It has a data labeling service. It has a deep learning VM images, so optimized for deep learning purposes. It has fully managed notebooks. So, I mean, essentially Jupyter notebooks, which you spin up, and then you can just connect those notebooks to your deep learning VMs. It has built-in algorithms, and that means the commonly used algorithms, yes, they are there, but it has, more importantly, hyperparameter tuning algorithms. So if you want to leverage the built-in algorithms for hyperparameter tuning, you will not be concerned with dealing with hyperparameter tuning yourself. Then it has a training service using which you can train your machine learning model, any custom machine learning model, scale it, select the underlying infrastructure for training purposes, and then there's a prediction service which will help you, for example, deploy your machine learning model and serve it. Now, all of this is complemented by AI Hub. So AI Hub is a repository for machine learning assets. So think about AI Hub as a GitHub repository, right? Where you can simply plug and play different notebooks, different developed machine learning models, this different pipelines, etc. And on top of that, this entire platform is also complemented or supported by Kubeflow. It means that you're not confined to GCP. You can build your machine learning models. If you don't want to use training service from AI platform, you can use Kubeflow to train it on premise or train it on some other cloud vendor. If you don't want to deploy and serve using the prediction service from AI platform, you can use Kubeflow to take the exact same application model workflow and deploy it on premise on some other platform. So there is a complete hybrid approach in terms of a cloud AI platform. So I'm just going to skip over here as well. So let's just quickly walk through those elements really quickly. So we talked about 6 core services for AI platform. The first one is the data labeling service. Sorry. So you can label your training data for machine learning. It has a graphical way, and you can combine that with data transformations using Apache Beam, for example. Or I mean, if you want to work with managed Apache Beam, then you can work with Cloud Data Flow. You can integrate that with, let's say, messaging queue like Kafka, or if you want to do with a managed version, you can use it with Cloud PubSub. So, I mean, all the integrations are open. In terms of the second element, which was the deep learning VM images, the idea is that these are just one-click installs, and you specify whether you want to have CPU, GPUs, TPUs. They come with the necessary libraries installed, but you can always bring in your own base image, and then you can spin up a deep learning VM image of your own. And again, I mean, we talked about AI Hub. You can push these images to AI Hub as well. That way, I mean, within your organization or within community, anyone can leverage or get benefit from whatever you have developed as a specialized deep learning VM image with some custom libraries and so on. So the third element, as I mentioned, was the fully managed notebooks. Supports the typical culprits of TensorFlow, Keras, PyTorch, scikit-learn, and so on and so forth. This is where, I mean, you can do a bunch of some very nice things. So you can, for example, plug and play any developed content on AI from AI Hub. So it means that if you like a certain algorithm, certain pipeline, or certain notebook, you can simply import it into your notebook. You can publish it to AI Hub from this notebook as well. And when you're working on your notebook, you have the flexibility to spin up any deep learning VM, scale the deep learning VMs, and through these proxy connections, connect your notebook to your deep learning VMs. Even from there, you can package your solution, package your machine learning model, and then publish it through Kubeflow on-premise, or you can use, for example, the prediction service to deploy it on GCP using AI platform. So again, it's a pretty open solution. The fourth element of the AI platform was the built-in model. So again, I mean, the common algorithms are there if you want to leverage on them. But I think the most important one is the hyperparameter tuning. So meaning that, I mean, you won't have to deal with hyperparameters yourself if you don't want to, and these built-in models can take care of those things. And the way it is designed, it's designed with a concept of containers, of course. It means that you can build your own custom algorithms, and those algorithms essentially run as containers. So there is no limitations of any sort. So you can think about, for example, think about your own hyperparameter tuning methodology. Think about some other customized algorithm. You can simply publish it as part of built-in models in a platform as well. Fifth element was the training service, essentially a serverless training using AI platform. You simply specify how much resources you want to give your training service to, and the entire infrastructure management for training is taken care by GCP. And similarly, as I mentioned, that everything is supported by Kubeflow. And the idea is that there are a bunch of machine learning microservices, training services, prediction services, and we have created this abstraction of execution environment and those services. It means that same way you would do a serverless training on AI platform using AI platform's training service, you can use Kubeflow to train or push that training to on-premise or anywhere you install Kubeflow. Again, Kubeflow is an open source, so yeah, so there's like no limitation. So I mean, I draw parallels with Kubernetes. So we open source Kubernetes, and now I mean you can work on containers, and then you can deploy wherever you want to. And of course, the control plane can change. Similarly here as well. I mean, you can have a control plane within a platform, but your entire training happens on premise or anywhere else you want to. Now, when you're doing that training, you want to have tools to compare, analyze, and I mean, the entire AI platform is augmented by TensorFlow extended tools. So yeah, you have all the typical metrics available for you to observe. You can check different configurations, different code changes, and so on and so forth. So yeah, I think there's nothing special over here. And then the last element was the deployment aspect. So either you do deployment using AI platforms prediction service, or again, you can also do the deployment on-premise or somewhere else using Kubeflow. So I mean, you can either create, I mean, like let's say online endpoints which are very low latency, or you can create endpoints which are geared towards massive or batch level predictions. So I mean, the entire scalability is taken care of. If, let's say, your traffic increases, you're not concerned with the serving infrastructure scalability. All those things are taken care of by the platform itself. So in short, if you are a data scientist, you don't want to work with AutoML. You want to have a full control. You think that the machine learning APIs do not serve your purpose, then you can work with machine learning from scratch yourself. I mean, you have, through AI platform notebooks, you can spin up your own deep learning VMs, create VMs of your own, do the training and prediction on GCP in a completely serverless fashion, or you can use Kubeflow if you want to do it outside GCP as well. So moving on to Cloud AI Hub. So I talked about Cloud AI Hub very briefly. So I think a very simple example for Cloud AI Hub is GitHub. So we built AI Hub with an intention that it will be a unified or one big repository for ML assets. And what it means is that you can host notebooks from AI Hub. You can publish your models in AI Hub. You can create your machine learning pipelines, and we will talk about pipelines in a bit as well, in the AI Hub. From the AI Hub, when you, let's say, search for a model which you want to reuse, you can simply deploy it in your own notebook. You can simply deploy it through Kubeflow or somewhere else, etc. So it's like an app store for machine learning assets. And I mean, we are seeing a very good response for AI Hub. And I mean, again, I mean, one question which we always get asked, I mean, how about controlling the private and public content? So, I mean, whatever we do from Google AI perspective, I mean, we mostly publish it as a public content. Our partners do the same thing. But same like GitHub, you can have, the same like you have a GitHub Enterprise, you can have a private content of AI Hub as well. So it means that you as an organization have a control of where your models are visible. If it's completely internal within your organization, you can have a full control. But if you want to make it public for the benefit of other community members, you can do that as well. So, I mean, if we try to draw parallels, so Play Store, Android Play Store, we have AI Hub for machine learning purposes. The Android SDK and OS. Now, I mean, any vendor can essentially implement them, build their devices, and ML pipelines like Kubeflow is in the same vein. So if I mean Azure supports Kubeflow, then yes, I mean then you can have you can run your training jobs or prediction jobs from Azure or AWS. I mean you can still do that, but you have to install those things yourself. Uh, there are Google mobile services for you to build your applications on Android, and there are GCP services to build your machine learning solutions. Uh, and then, I mean, from a hardware perspective, I mean, you can have everything on a hardware Pixel phone or some other Android phone. In this case, we have a GCP infrastructure. Right. So moving on to Kubeflow. So I have a lots of content. So Kubeflow, this is an open source project. The idea of the Kubeflow, and I think it will hopefully be clear in next 5 minutes or so. The idea of the Kubeflow is that machine learning problems, you are dealing with a bunch of steps. I mean, pre-processing step, distribution normalization steps, cross-validation steps, and so on and so forth. So we wanted to build a solution, which is cross-platform, not limited to GCP alone, but also gives the flexibility that you can plug and play different components, just like a Lego pieces, and then construct your pipeline. I think let's just look into examples. So what exactly is a pipeline? So in this example, I have a pipeline, pre-process my data, do the feature extraction, run 3 different types of machine learning models, validate those models, and then push those models to serving, right? So there's one key aspect which I would like to highlight, that all these tasks and components, they are essentially different containers. It means that, again, I mean, those details are not visible to developers. But the reason why this is important is that this does not bind you to a single framework or a single language. For example, I mean, you can do the pre-processing using pandas. You can have one machine learning model implemented using TensorFlow. You can have a second machine learning model implemented, for example, through Keras or something else, and so on. You can have multiple versions. So I mean, unlike some other applications, you're not tied to a specific version, specific library, specific framework. Your entire tasks, your tasks can be using different libraries, different versions, and so on. So this abstraction makes the portability extremely important. And that's why, I mean, when you build up a Kubeflow pipeline, this sort of a pipeline, you can run it on premise by installing Kubeflow. You can run it within GCP. You can run it outside GCP. So I mean, this is why we created this sort of an abstraction, so that there is no vendor lock-in per se, right? And this makes the entire life cycle a bit simpler as well. I mean, now, I mean, you connect to a DB, you'll create a data set, you do feature engineering that we talked about earlier, uh, train a machine learning model, do hyperparameter tuning, publish a machine learning model, and then your developer builds up a logic to consume. I mean, if you have matured that pipeline, then there is no need for these intermediate steps. You can simply plug in that pipeline, deploy that pipeline, and your developers can start consuming it. Again, this is easier said than done, and this is why we found that there is one gap still in the machine learning. And this is where, I mean, we talk about end-to-end machine learning. I think this is where now we are heading towards. This is where ML ops become important, right? So ML ops. So think about DevOps, but for machine learning, right? But machine learning has very different sets of challenges compared to DevOps for modern applications, right? For example, I mean, think about it like this, that machine learning today has a lots of manual steps. right? And machine learning has to be constantly retrained whenever there's a new data or a new trigger of data, right? Uh, for machine learning purposes, serving skew, training serving skew is extremely important. So imagine a situation where you have deployed a machine learning model. You are expecting speed as a parameter, as a feature in kilometers per hour, but suddenly your production system starts sending miles per hour. A small mistake somewhere else within the system, and that creates a big issue. So there are challenges, additional challenges for machine learning to have a DevOps-like approach for machine learning. So let's just go through them and then let's see, how we solve it. And this is coming from our experiences. This is how we manage these large-scale machine learning deployments. So this is a very famous image from a paper from Google in 2015, Hidden Technical Debts of Machine Learning Systems. So essentially, the point of that paper is that machine learning code will always be a small piece of the puzzle. It's always the external configurations, data collection aspects, monitoring, data validation, and so on. Creating the infrastructure for serving and so on. So there's a lots of things surrounding machine learning. It's not just the machine learning model development alone. And the way we do it today, I think this is important to understand before we talk about how we solve it in future or how we solve it now, is that we start with the exploratory data analysis. Um, then data scientists do all these steps manually. The things that we've talked about: data preparation, feature engineering, normalization of data, creating a sampling strategy. So they do all those things manually, followed by model training. So they pick up a machine learning model, they train it, do hyperparameter tuning, all that fun stuff. They do the model evaluation, they do the cross validation. This process is iterative, and in the end, we have hopefully a trained machine learning model, which we push to some sort of a repository, and then IT takes over. They are responsible for serving the machine learning model, and right now there is no feedback loop. So this is why I was in the beginning of the talk, I said that the feedback loop hasn't been solved formally or properly till now. Now, what are the issues with this approach? It's time consuming, it is manual, it is error prone. We talked about training serving skew. Any miscoordination or lack of coordination would mean that your performance and your actual results would be different. It is not reusable, and so on. How do we solve this situation? So, one proposal is that we create a higher level framework for ML ops. We have a very separate sort of elements for training and serving. Now, when we talk about these four different segments, and we will talk about how we solve those different things. The first and foremost is the experimentation and the development, right? So, and this is, extremely crucial because, of course, in the end, data science or data scientists are the guys who will end up creating those experimentations, deployments. So that element will always be there. Now, how we want to improve that element is by introducing continuous training, because if you remember, we talked about getting this feedback loop. So we would like to have this experimentation or development in a way where we can have a continuous training happening on our machine learning models. In terms of serving, we also want to have the model properly tested, evaluated, etc., the typical CI/CD steps. And lastly, we also continuous monitoring, and that continuous monitoring provides a feedback loop for experimentation purposes and also for continuous training. So it means that we want to have a way where we can have the experimentation and development which can result in a continuous training, not something which data scientists have to do manually, but rather something which can happen automatically. And we also combine everything through a feedback loop. Now, the way we do it and is the following: that first of all, we orchestrate the experimentation or the development of these pipelines. So for, let's say, In this case, we have data extraction, data validation. We have, for example, model training, model evaluation. So right now, we have not done any development. This is just a skeleton. This is just the specification of how I will orchestrate my experimentation process. Right? There's been no code writing at this point in time. Once we have that artifact available, the training pipeline will kick in. Now, training pipeline has a bunch of predefined steps like building components, running automated tests, storing those artifacts, and deploying to a target environment. Right. So, and this will result to an artifact store. And once we have these two orchestrations ready, then we can essentially do continuous training. And in this continuous training is essentially the instantiation of our orchestrated experimentation. So the steps or the workflow we defined to develop a machine learning model all the way from data extraction to model validation is being trained constantly. That's where the feedback loop comes into picture. We bring in the training data set. This is the end. This results in trained machine learning models. Now, when we have the trained machine learning models, so in our source repository, so our source repository was the place where we had the orchestration of our experimentation workflow, and our model registry was the result of continuous training. So it has the trained machine learning models. The model deployment CI/CD using the same services as I showed earlier, building components, running those tests, etc., will perform the CI/CD on your machine learning models, and it will end up dealing with the serving infrastructure. Right? It means that the serving infrastructure is responsible for predicting, explaining the results, evaluation, monitoring, and so on and so forth. Right? And this is where your live data kicks in as well. So far, everything looks very abstract, right? Now, if we look this new process as a whole, right? Again, I will tie everything up through services as well. So if we look everything as a whole, so we talked about experimentation and development orchestration. This is essentially a workflow development, right? That workflow is available in some sort of a code repository. So this is essentially a set of configurations, how my pipeline looks like. Then there's a training pipeline, right, which knows how to build, how to run my test cases, etc., etc. Then there's this continuous pipeline, which on the basis of the orchestrated experimentation and the training pipeline will constantly keep running the training. So this process gets completely automated, which results in the trained model, which are then picked up by the deployment CI/CD that will deal with the serving layer, the infrastructure, etc., and so on. And the glue for this entire thing is the ML metadata, right? So that serves as a glue. So now, given this sort of process for end-to-end machine learning, again, and this is something we're talking about production-grade machine learning solutions and so on. We if we take the representation something like this, that we have a business case. We have, let's say, a data lake as a repository of my data. Data scientists come into play. They bring in their data science platform, and now we talk about different elements. Talk about data pipeline. We talk about the orchestration of experimentation workflow. We talked about a pipeline for training purposes. We talked about a pipeline for deployment purposes. We talked about monitoring. We talked about content training, and so on and so forth. Right. So this is all what we need, and this is how we solve this. So you have feature store, which you can use to orchestrate your experimentation or development of a machine learning solution, right? And now feature store works directly with works directly with your notebooks. So let's say when the data scientists are working on the notebooks, they are performing a bunch of those different steps. They can publish those steps in a feature store. So there is a specific way where those things can be done. It means that In a very simplistic, naive way, we can think about feature store automating the entire notebook. Again, this is probably not the correct interpretation, but this is a simple way of thinking about it this way. That data scientists have created this notebook model, a validation scheme, etc., and the it's codified into feature store. Now, feature store has the orchestration of experimentation, right? Then, if you remember, we talked about the training pipeline, right? And the training pipeline contained a bunch of steps. Sorry, I have to go back. So the training pipeline contained knew about some of those steps, building those components, running the tests, storing the artifacts, deploying the target to environment, and so on and so forth. This is where the service, sorry, here you go. This is where AI platform experiments come into play. So they essentially implement all those services. So you're not concerned with uh, managing the training pipeline on your own. AI platform experiments will handle that on your behalf. Then we talk about continuous training. The AI platform training service is already there, and that serves that purpose as well. Then we talked about having the model CI/CD. This is where the AI platform prediction service is there. Then we talked about the continuous monitoring, and that's where AI platform continuous evaluation is there. So, and I mean everything is glued to machine learning pipelines and machine learning metadata. So it means that we can essentially implement this process in which we let data scientists do the experimentation, push that experimentation recipe to feature store, which is essentially the training pipeline. I mean, the CI/CD pipeline for training purposes. Then there's a service which picks up that artifact and is in a constant training mode by taking any external triggers, any additional new data, or any feedback loop from your production systems. Then you have the CI/CD for model deployment, the service which handles the serving layer, and that service is there already. So by doing or expressing the entire end-to-end machine learning problem in this way, we can optimize the highly manual machine learning development process. So, and that essentially what ML Ops is all about. So to do a quick recap, I think we covered a lot today. Um, from an AI perspective, we are trying to cater for different levels of expertise, right? I think, I mean, okay, so let's skip about the services and solution aspect. We talked about the pre-trained machine learning models. I mean, if I am starting something new, I mean, and as I shared some of my experiences, those pre-trained models work very well, at least in the beginning phase, when you have a bunch of images, bunch of some tabular data, some video files, for example, some speech. You may not know what is possible with your data. You might not know what structure is there. So, me running through some of those APIs, passing your data to these APIs will reveal a lot about your data. Right? Like I gave the example, I was skeptical about that project. We use Vision API. It gave us lots of other ideas that were possible. Of course, I mean that's not the end goal. Um, that will help you start your machine learning journey, but eventually you want to build your own custom machine learning model, right? And again, as a first step, you can move on to AutoML. Let the service figure out which machine learning model is most suitable for your data. Let the service figure out the training aspect, deployment aspect, scalability of serving, and so on and so forth. You simply, given your data, let it build a custom machine learning model based on your custom data, and then simply consume that data through REST API. And then, of course, when things get mature enough, then of course you can go to a full data science experience where you have the AI platform with all these services from deep learning VMs to data labeling to prediction services and so on and so forth. So then you have a full flexibility, full control over what you want to develop. And then, I mean, the end, of course, at a later stage, when you want to dive into more CI/CD paradigm for machine learning, you have machine learning ops, uh, DevOps, customized for machine learning. You have ML pipelines, ML metadata, and everything is, as I mentioned, supplemented or complemented by AI Hub. So, I mean, published content over there. We use Kubeflow pipelines, build Kubeflow pipelines, and by leveraging the Kubeflow and Kubeflow pipelines, you can essentially do all these things outside GCP as well. So this essentially is a view of all those different services that we have talked about today. Um, yeah, so I think that was pretty much it from my side. Um, we have 3 minutes, so I don't know if there's enough time for questions, but if you have any questions, please do. Designing block for synthetic data. Um, no real built-in module for synthetic data. There are a couple of, I would say, initiatives or projects. I mean, if you drop me your email address or something, I can get back uh, as to what I can share along those lines. Uh, those things are not really public at the moment, but I can definitely check on my side. Just drop me your email and I will do a follow up with you. Because if there are no further questions, then thank you so much. I hope you learned, yeah, learned something. I mean, at least I learned a lot in this experience. And I mean, as I said, I mean that I've been on both sides. It's lots of things we learn the hard way. So yeah, I mean there are some mistakes we all have to do in the end uh, to get a bit of a wisdom. So thank you so much.